Hi, I'm Sonia Kolasinska, and today I'm going to be showing you low latency stuff. Low latency GAL presents low latency stuff. Let me start with about myself. So I do software engineering for 25 years as a professional engineer, but I started my adventure with computers when I was like 6 years old. My first program I wrote when I was 8 years old. It was BASIC on static spectrum. I did some assembly programming when I was 19. I did a 3D rendering engine in assembly. I did some game development framework, which is open source on my GitHub. I did some distributed framework for poker bots playing on the server. And then I did a high-frequency trading engine, trading engine. So that's quite a lot of background from the beginning of my career. There's much more after that. Let me just go in straight into the topic. So thread synchronization one-on-one. Let's just start with basics. So when we talk about multi-threaded applications, we always think about mutex, conditional variable. We don't really realize, but these two together, they basically constitute a monitor. So when you have mutex and conditional variables, they live inside of a monitor, which you can compare to dental clinic. Let me just tell you what dental clinic is about. Like we probably know, right? So a patient comes into reception, gets the ticket, goes into waiting room. And in the waiting room, it checks if the door is open for the treatment room. If it's open, if there is a doctor, maybe they go in and they lock the door. If there is next patients coming into the waiting room, they have to wait until the patients that entered have left. So what we're having here is a door, is a lock that just prevents other patients from going into the treatment room. And then when you finish, we leave treatment room, you open the door, and the nurse calls the next one. So that nurse calling the next one is a conditional variable being signaled. And what happens next? All the patients waiting in waiting room check who's next in the queue. So that's the checking of the condition. And then one that checked says, yeah, that's me, goes in, locks the door, and it's the next patient. So more or less, you can imagine this way. It's not exactly that way, but let's imagine this way. Now, what is lock? Lock is a barrier that only allows one thread to enter critical section, the code of which may modify at least one piece of shared data or read multiple pieces of shared data. We will talk about this on examples, so I will just read this now. Wait is an inactive state of the thread, where thread execution is suspended until lock becomes available, conditional variable is signaled, blocking operation has completed, for example, reading file. The problems of locks and wait. Lock is a barrier that stops other thread from making progress until thread holding lock releases the lock. That's one problem. Deadlock is also possible when two threads cross-lock each other. Wait is an inactive state which causes inexpensive thread context switch, right? So they're expensive, they block each other, and so on. So what is lock-free, wait-free? It's going to be something that at least one thread always makes progress. No thread will enter inactive suspended state. And we achieve ultra-low nanosecond range latency. Yes, nanosecond. And the cons, of course, is we eat CPU. Lock-free is a method of programming where atomic instructions are guaranteed that only one thread will modify shared data at the time, and data will stay consistent. So this is what replaces the lock, the atomic instructions. Wait-free is a method of programming where atomic instructions guarantee that a thread can wait for a condition to be true. So that's how we replace this entry to inactive suspended state. Cache coherency, one-on-one. So again, I'm just going to read. Cache coherency is an algorithm implemented by CPU to maintain consistent view of data at a given memory address. And memory barrier is an internal mechanism in CPU to enforce cache coherency when we perform reads and writes on volatile data. Let me show you something. This is some assembly code of Intel x86. Now, normally move EX the word pointer, the blue instruction is loading value from address EDX into register EX. It's just reading the variable into CPU. Next, it's testing it against 0. Test EX is tested against 0. And if it's not 0, try again. So it's a loop that keeps testing a variable against 0. And if it's not 0, it keeps looping. Now, we inserted memory fence here. This is the memory barrier. So what happens without this memory barrier? When we keep reading this address under EDX in a loop, we send into memory control pipeline in CPU those instructions to load from this address the content of memory. And we don't know when it executes it and what will be the state of a cache that CPU has. So it would probably be reading same value all the time for a long time, and maybe it would get delayed. This actual new value that some other core has written would be delayed on this reading. If you put memory fence in there, then we stop this read. So what happens is we send into this memory controller unit this memory fence and the load from the address, and then memory fence and load from the address, and memory fence and load from the address. And when we do that, we tell the memory control unit that it is not permitted to proceed with the next load from the same address until the memory fence finishes. The memory fence waits for cache coherency to complete. This is the ARM version of this code, DMB-ISH. ARM is pretty interesting. ARM has a very broad understanding of what memory barrier is. So DMB is classical memory barrier, where we just talk about memory barrier. DSB is an instruction data synchronization barrier. So it means that it's a memory barrier together with the instructions that follow. So this next instruction, for example, in this case, CBNZ, would also be stopped from execution before we can continue with DMB, right? But DSB. Sorry. So what happens here is we load with LDR X0 from address X8, and then we test X0 register against 0, CBNZ test against 0 that register. If it's not 0, NZ means not 0, jump to try again, and we keep looping, right? So this is more or less the assembly. Now let's look at the picture. The cache coherency on the picture looks like this. CPU core number 1 is writing to memory. How is it writing to memory? It's actually not writing to any memory. It's shown on the picture that this may happen with dashed arrow, but generally core 1 is writing to level 1 cache, then it writes to level 2 cache, then it writes to level 3 cache. And then cache coherency propagates this into level 2 cache core 2, level 1 cache core 2. Now the propagation is a very complex mechanism. It can have different algorithms, and it can be implemented using a dirty flag. It can be implemented during the push of the data, whatsoever. It doesn't matter. For us programmers, what matters is that the core 2 may, for example, choose to wait until this whole synchronization happens using the memory barrier. So what is compare and swap? Compare and swap, well, it solves the problem, right? So we have an assembly code here which has a race condition. And the race condition here is this mov EX dword pointer EDX and mov dword pointer EDX EX. So the blue instruction is reading from address EDX some value, read some variable X into CPU. And then the yellow instruction is saving into the memory under this address EDX the value of this EX register. We change the value under EX register in add EX EBX. So this is the computation. So you can see that what we're saving with the yellow instructions depends on what we're reading with the blue instructions. And now if we'd have two threads doing this, two CPU cores executing this in parallel, then we will have one CPU core, for example, executing a blue instruction. Second CPU core is executing green instruction in add EX, EBX. And then it's execute mov dword pointer EDX, EX, writing this new value based on the value read from blue mov EX dword pointer EDX. And the other CPU has the old view of this memory address, and it will overwrite computed value based on the old view. So what happens here, the core that was kind of first to read the old data, it's now second to write, so the data that's in memory is not consistent, right? Because we're overwriting the new data with the old data or something like that. So it's just inconsistent, the wrong result. So here we've got a thread save operation. It's compare and swap. So what happens here, we do exactly the same thing, except that now we have this log compare exchange EDX EX, which will write to memory only if other core didn't write to the same address in the meantime. So if our core, if thread running on our core was doing mov.ex dot pointer edx, so reading from this address and then doing computation, and now it's writing to this address, and no one else was touching this address, it will be successful. But if some other thread did something similar and changed the value under this address, our thread needs to repeat the operation, and this way we will not corrupt the data. We will not have inconsistent data, right? So this is Intel. On ARM, it looks like this. ARM is slightly different. On ARM, there is no compare exchange. So first of all, this is race condition code. This is without compare exchange code. And we can see on ARM, the instruction to load is LDR and to store is STR. The concurrent swap version of this, which is actually kind of transactional memory thing more than concurrent swap. So what we have here is LDAXR. So remember that it was LDR, and now we have LDAXR. It was STR, and now it's STLXR. So this additional AX and LX, this this is acquired memory, and LX is release memory. So that means that when we do LDAXR, ARM processor will acquire that memory address. This core will say, I'm now owning this address, and that's the computation. And now the store will say, release my ownership of this address. So it's kind of like a tiny lock inside the CPU. But because this STLXR can actually fail, the X9 will contain whether it failed or not, it's not actually exclusive. This is not actually a lock. It's just a monitoring. It's just passive monitoring of this memory. And if other core changes, you see the CBNZ X9 try again will jump, and we try again. So this is essentially like a compare and swap kind of thing. It's a transaction that gets rolled back if there was a change done by other thread. All right, so this is picture. We have CPU core number 1 doing compare and swap and CPU core number 2 doing compare and swap. And we can see that CPU core number 2 has cache rejected. So they were doing at the same time, and one of them was the winner, and the winner was core number 1. We can see how cache coherency propagated to level 1 cache of core 2, and we got the rejection there when a second core tried to write at the same address. Okay, so what is synchronous concurrency? Synchronous concurrency, I'll explain on this example. So we have here a data structure, which would be a very classical example, I think, for showing race conditions in maybe C++. So this data structure contains, well, it's a class, right? But it contains two fields, two doubles. One is total sum and one is total count. Now, what we do here is we calculate average by dividing total sum by total count. We can immediately see that average is dependent on reading two variables. So this is two reads. And as we remember from assembly code, two reads is two instructions. And two instructions means that there is a race condition, right? Add value, on the other hand, will be two reads and two writes and two computations. So that's 6 instructions, and that's definitely a race condition, right? So what do we need to do to make it multi-threaded? We need to put a lock. We can use mutex. Mutex is a thing that will enter operating system when you lock, and you have to wait. Means that it is not nice because we are waiting, we are swapping the context of current thread, so that will be expensive. And on top of that, it is a lock, meaning that the get average will serialize, meaning that if you have 100 threads doing the get average, you will actually only have one thread doing the get average, and then 99 threads will be just sleeping in this inactive state. Here's the solution of lock. Here's the solution of wait. This code is wait-free, but it is not lock-free. So it's using a spin lock, which is a lock, right? So the get average will still block other threads, but it is wait-free because spin lock never enters this expensive waiting state in operating system, inactive state, right? So how this solution is, better than the other? It's actually worse. And I tell you how. If you have 100 threads doing get average, then, if you have, for example, 4 cores in your CPU, the first core might enter the code of this get average. Second 3 cores might be spinning, doing the spinning on those spin locks. And the remaining, there was 100, that was -4, so 96 threads. I don't know what they will be doing. It really depends, how operating system will schedule this. It will probably hang up the computer because every of these threads will try to use 100% CPU, basically. So there is a problem with this lock, right? So let's solve this problem. Let's get rid of the locks completely. Let's make it lock-free and wait-free and forget about any locks and make it thread-safe whatsoever. So here we have this const star volatile. That's quite amazing, right? So what we actually have is a pointer. The pointer itself is volatile, meaning that it can change across threads. So I'm reading a pointer and some other thread is changing it while I'm reading it. And it's a pointer to a const basic stats, meaning that the stats are constant. No thread will ever change those stats. So what is possible to change is a pointer, but the stats that it's pointing to are never changing. It's a const. And the benefit here is that, well, once we have a pointer to those const stats, we can read it and no other thread will, do some damage to the data that we're reading, right? Quite not really here in this code. Let's look at this code closely. So get average gets a pointer, current version of a pointer, right? Because it's a volatile MP data, so it's a current version, and the new version is in doing, right? There's some other thread creating new version of this pointer, but we already read this old pointer and we're getting the average, and we're happy with this average. However, we're still calculating this average, and this other thread, what it's doing, it's creating new instance of this basic stats, copying data from under what was the previous pointer of MP data, and updates this local basic stats. It's local, so it's not on stack, it's on a heap, but it's local in terms of thread. So this thread is the one and only thread that has access to this basic stats. So it can modify it. It's not const in this context, right? But the next thing we do, we publish it as a const, basic stats into this MP data. And this way, how other threads will see it while they do get average. So this moment when we publish is the moment when get average will start returning the new pointer. We publish using this, in this case, Windows NT function interlock compare exchange pointer, which is an atomic compare and swap operation on the pointer. And it also will perform memory barrier for us because all those atomic operations do perform memory barrier. Now, there is a problem here. Once we do that, we delete the old pointer. What is if there was a thread doing the get average, and the pointer it got was the old pointer? Well, it's using the after free, right? So using deleted object. That's not nice, right? So we have a use after free here. This solution doesn't work. Now we have another problem here. Operator new. Operator new will enter C runtime, C++ runtime. And C++ runtime will probably use some kind of locking to allocate memory and who knows what else. So that's a really, really bad solution. Anyway, we wanted to have a lock-free wait-C solution and we ended up with some really terrible solution. Let's go ahead. Let's see what we can do. So, so here we solve the solution with, so here we solve the problem with shared pointer. So which problem do we actually solve? We solve the use after free. So what happens here, we use shared pointer to prevent deletion if someone else is using the object. So what that means is get average will acquire more references, will acquire one reference. So every thread doing get average will acquire one reference. If there's 10 threads doing get average, there will be 10 more references to this MP data. And they use atomic load for that. So it is important that shared pointer itself is not atomic, and you cannot be doing that. You have to use either lock to read the shared pointer or atomic load. Then in add value, we repeat the code from the previous example, but just using shared pointer. So we use atomic load and we use atomic compare exchange strong instead of this Windows interlock exchange. But we have problems. Problems are spin locks. And the problem is that the atomic load in the implementation, at least of Microsoft Visual Studio, the version, at least, I'm not sure which one version I was looking at, was using global spin lock. And that is not really exactly what you want with atomic load on shared pointer. In general, you don't want your atomic functions to use any spin locks, right? Another problem is the make shared is still using memory allocation. It's still using new. So it's still not going to be amazing. So this solution is not solving that much problems. Let's go ahead and see what else can we do. This is a C code, and this is actually example from my project. It's on my GitHub. It's called lock-free. This is called NT-ARC. I was inspired by Rust ARC. ARC is an acronym for Atomic Reference Count. So ARC itself has atomic reference count, but it's not atomic on its own. You cannot load it atomically or store it automatically, and store it atomically. However, in this library, I created a number of functions. I would call them methods because this is object-oriented programming in C. So we have here anti-atomic store and anti-atomic load. Those methods are performing atomic store and load on this anti-arc in an atomic fashion. So even though it is like a shared pointer, it has a proper atomic store and load, and it uses 128-bit concurrent swap operation. So that's why it's possible. Now, what this code is doing here, we have local variable anti-arc in make-foo, which acts as a local, instance of shared pointer, local variable of type shared pointer. And then at the end of this function, we have anti-arc drop, which is essentially explicitly calling, because this is C, a destructor of this local variable, right? So when we construct a local variable, in this case, it has no references, then foo new is like make shared. It will just put into this anti-arc a new object. Then we do anti-atomic store. So we copy the foo variable that's local into global variable gfoo, which is also anti-arc. So that's like assigning a shared pointer using atomic store. And then atomic drop will destruct our local foo. So that's essentially object-oriented C++ kind of inspired, right? Construction and destruction. But we have this nice atomic load and store. Okay, let's look at hypothetical C++ code. So that might be in some future some new library, who knows, based off my anti-arc, or maybe written completely in C++. So imagine that this log3 arc basic stats const is anti-arc based solution in C++. That does exactly the same thing in C++. And then there is a new thing that I have not yet implemented, and I just noticed it by creating those slides. My anti-arc does not have compare store. It only has atomic store, but it doesn't have compare store, and I have to add it. And I don't think it will be complicated, but I have to add it. So rest is looking more or less the same as, the shared pointer version. It's just, here we've got atomic clone instead of atomic load. And I don't know, I just thought maybe that sounds more like what it should be called. And then we have this atomic compare and store, right? It is completely log-free and weight-free solution. And there is no problem with allocations, because as well additional feature here we can see is a log-free free list. Free list which could be implemented log-free using, for example, single linked list and some compare and swap. And all you need to do is chop off the head every time you allocate and put back on the head when you deallocate. That's all you probably need to do. And you achieve complete log freeness, weight freeness, and you can spin in this do while as many times as you want without costly allocations. You can leave this do while without the use after free, and everyone is happy. 100 threads bashing through get average, no problems whatsoever. So this is the solution to go. Now, asynchronous concurrency. We had synchronous concurrency. What was synchronous? We were accessing from multiple threads same data. In asynchronous concurrency, we'll be accessing we'll be sending messages. We'll be having queue. We'll be sending data through the queue. So one thread will be putting something into the queue, other thread will be removing something from the queue. So this is an example of the queue. It would have enqueue and the queue. We have here on the right side two threads, producer and consumer. We have this making, processing, which are just some user function to produce some data and consume some data. Here we've got the producer and consumer definition. Producer runs a loop. It creates items and puts them into the queue. Consumer is the queuing item and processes them. These are the concept that I use there. So this is queue concept. Queue concept contains element type. It contains enqueue, which takes element type, and dequeue, which returns element type. Now, this is a typical unbounded queue multi-threaded. So this is what you would normally write in very, very 99% of cases. And you don't have to write it. You can copy paste this code because this is the way to do it. Now, this queue here has enqueue, which uses a lock, then places at the back of the container, right? And then the lock ends, and it notifies other threads that were waiting on the condition that there is at least one item in the queue. And that queue is using lock in order to await on condition. So again, this is like this dental clinic. So this lock in the beginning is something that was hard for me to show in this dental clinic because we need to acquire it. Maybe it is like they go to this reception and they there's only one person in this reception to get the ticket and moves to the waiting room, and this is how this lock gets acquired for just one moment. And the moment you go to the waiting room, it's the condition variable wait. So this is when we release the lock immediately. So this lock was acquired for a moment just to get this ticket and go to the waiting room. Now, condition wait is gonna wait until as long as the queue is empty. So when it stops being empty, it will continue into the code below, and we will pop the first element from the queue and return it, right? So problems we see here is that locks, as usual, cause context switch, conditional variable causes context switch, and notify one is a wake-up call, which is also doing something on conditional variable, which is, not necessarily wait-free and lock-free, so it's definitely doing something costly. So this is not low latency, this is slow, but this is very useful, very nice data structure to have. Now, this one is faster. This one is way faster. This one is a bounded queue. And we sometimes use bounded queue. And this is usually built of two semaphores, okay, two counting semaphores. One semaphore is counting how many available elements are for processing. And another one is counting how many free spaces are there for writing new elements. So in the beginning, when we create this bounded queue, there is n, because n is this size of this queue, right? It's bounded by this size n. So there is n elements available for writing and 0 elements for reading, right? So this is empty queue, nothing for reading. All queue is available for writing. So to enqueue, we acquire one element from semaphore counting elements for writing, free spaces for writing, and then we put the element into space calculated, this mWrite post, which is actually atomic size t. I use that so that multiple threads can call enqueue at the same time in parallel, and there's no problem at all. We put the element into that position, and then we release the other semaphore. So we acquire one semaphore and we release the other semaphore. That's kind of like how this works, right? We release the semaphore that counts number of available elements for reading, right? And then the dequeue is acquiring semaphore counting number of elements for reading, calculates the position to read using this atomic size t, and reads the value from that position and releases the semaphore so that now there is more spaces for writing again. So that's a very basic, very, classic implementation, I think, of the bounded queue. And I have created something that's ultra low latency based off exactly this design. So all you need to do in this design to make it ultra low latency is that you replace this awful context switches, which is, in case of semaphore, it could be 700 microseconds, 700 nanoseconds. So you can replace that with something that takes no more than 100 nanoseconds, or even 10 nanoseconds. So let's replace it. Let's see what I replaced it with. So I replaced it with entering B. Entering B is a solution in C I created. It's again object-oriented programming in C. Sorry, where we have this entering B structure containing those two semaphores and two counting atomics. So in this implementation, there's no semaphores, there's no counting atomics, there's actually four atomic integers, four integers, just four integers. And I'm using compare and swap operations on those integers, atomic increments, to implement begin write and commit write operation. So what you can see here, this keep producing is a loop producing new items. Produce next value will generate new values, some user code, whatever code you want to put in there. And then begin write will reserve a slot for writing. So this is like acquisition of this semaphore counting number of spaces available for writing. And at the same time, it calculates for you position where you should be writing. Then there is a memory barrier because this begin write will use atomics. And then we have a memory copy, which is basically we take data from this global array in here G buffer, and we put this data into some local variable, right? And eventually, when we finish reading that, writing that fragment of buffer, we just say commit. When we say commit, it's like releasing this semaphore for reading. So now we just telling the other thread, oh, there is something to read, right? And consuming, consumer will keep consuming. So we will have begin read and commit read as well. We will do mem copy in between. We will also have these two memory bars. One thing that you need to notice here is entering B pause. Entering B pause is essentially a transaction. So in the C version, I just have a variable locally defined before the loop, and I'm reusing this in every iteration. So you can see when I do begin write, I'm reusing same ring B pause. I just initialize it once. But every time I'm doing begin write, it just creates a new transaction. And when I do commit, it finishes transaction, right? Let's imagine a C++ version of this code that never existed, and maybe I will create one at some stage. So basically, this is our bounded queue in C++, which would use entering B implemented in C++. But in C++, I can imagine that instead of entering B pause, I would have two different structures. One would be called ring boof write and ring boof read, which would be read transaction and write transaction. You have transact begin write and commit write, and then you have begin read and commit read. So essentially just prettier version of entering B, doing the same thing. And as you can see, in between begin write and commit write, we have the actual operation of writing. So if someone asks me about performance of this thing, the way this is implemented is that the begin write and commit write are just computing the integers using the atomics, and it's very, very simple operations using atomics. There isn't much that can be improved. Although you can try to see what you can squeeze there in, maybe with the, because these variables need to be in this. These are the shared variables between cores. If you wanna later on do pipelining, which I'm going to talk just in a moment, then you want this, that it will be shared between CPU cores in the cache, and maybe you can do some optimization with how they are stored. But anyway, that will be probably how this transact is stored, or how this mring boof is stored, right? If it just maybe aligned or something, then maybe it's better or something. I don't know. So long story short, this is user dependent how fast this is going to be. Your speed depends on how slow you're doing the m data pose modulo n equals move value, right? So that's your main slowness here. So if you move data value into the buffer or read value from the buffer, maybe you want to do something else in this time, you can do between begin write and commit write any other operations, or you can do some computation if you like. So that's what's the limitation. Okay, let's talk about pipelining. So pipelining is a method of organizing multiple threads so that the result of first thread is an input to the second thread, while first thread processes the first portion of an item, second processes the second portion of an item, right? So let's say that on a picture, but the items are basically split into portions. So if you normally would have single-threaded code that would just do process some one item starting by doing some number of steps, it will just do step 1, step 2, step 3, step 4. You can pipeline it so that step 1 is and step 2 on first part of the pipeline, and step 3 and 4 is on the second pipeline, and then step 1 of the second item can start earlier. I'll show you on a picture. Thread pinning is necessary, right? So this is essentially assigning exact CPU core to each thread. So CPU cores and operating system threads, they are completely disconnected, and there is multiple problems here going on. So operating system will assign your threads to any core, and if you don't pin it, then it will just jump between cores. That is very bad for cache, right? Second thing is, if you don't pin your thread to any specific core, then if you're doing atomic operations and do any sort of spinning, they will not be able to fully utilize the CPU core, because operating system will be moving your thread between cores and so on. So you need to set affinity to make sure that the thread and the core are the same thing, And here we go. Pipelining one-on-one in order processing. So we have here on the picture 2 CPU cores doing some action. The threads are attached to these cores using pinned, right? They're pinned to these cores. Core number 1 is processing some market data coming in from some device, let's say. Core number 2 is analyzing. So what happens is market data is processed, it goes into level 1 cache, item number 5, and so on, and to ring buffer. Ring buffer sits in level 3 cache. and we're writing fifth item. And at the same time as we're writing fifth item, the core number 2 is reading the fourth item. So you can see that there is this thing happening. You can see on the diagram below that the core number 1 is reading the fifth item, and core number 2 is the core number 1 is writing fifth item, and core number 2 is reading fourth item, right? We can also see where the pipelining has zero latency and when the pipelining is slightly delayed. However, just imagine stacking those into just one thread, and you'll see how much all of that will get delayed if you try to squeeze in those green stuff in between those orange stuff, right? So it will be you will get very delayed processing. Like item number 4 will be much delayed to start even, right? If you were to put all the green 1, green 2, and green 3 before it. So pipelining really gives you a lot of, improvement in processing of data when you have a stream of, high frequency data, right? Okay, so item number 1, item number 2, and item number 3 has pipelined with zero latency, whereas item number 4 had some delayed processing because item number 3 took a little longer and it ended processing on core number 2 after item number 1 finished on core number 1. So that's why item number 4 got delayed. But you would still get more delay if you were to put that in one thread, because item number 4 wouldn't even start before item number 3 is processed, right? Let's look at out-of-order processing. So how about we try to solve this problem by just having another co-processing items, and this way if item number 3 takes too much time, then item number 4 is processed by another core. Now we have zero latency everywhere, but we have out of order. This is out of order because, core number 2 will finish item number 3 after core number 3 finishes item number 4. So you might get into situations that you have out of order processing. Another problem that we can see on this diagram is the redness, lots of red spaces, and that core number 3 has a lot of red spaces before this item number 4, meaning that it's going to be spinning. The CPU core will be literally getting hot, doing no job, right? So that's essentially what this is. It's just spinning, doing no job, waiting for a job. So, that's not so great, right? Let's look at another diagram. So here we have split and merge solution. In this solution, we tried to fix the problem that item number 4 was finished before item number 3. So we introduced another ring buffer, right? And the cool thing is that these ring buffers have zero latency, so they just glue to each other, right? So we can see that item number 1 pipelined the same way as previously, and item number 2 and item number 3 now pipeline slightly differently. So how does it pipeline? Let's look again into item number 1. Item number 1 does first portion, right? It writes the result of the first portion into the ring buffer X. And then core number 2 is reading this item 1 from ring buffer X, and it's writing to ring buffer Z. It's writing to slot A. But how is it writing to slot A? It's slightly different than before. So as you remember, the transaction can be begin and committed at any time in this ring buffer. So if you begin transaction before, in the very beginning, you're actually reserving the slot. And what happens here with the item number 3 is that when item number 3 starts being processed by core number 2, the slot C is being reserved in the ring buffer Z. And then when item number 4 is processed in core number 3, the slot D is being reserved. And what happens is when item number 4 gets finished, it gets finished before item number 3 on core 2, but it tries to commit slot D. It tries to commit slot D. And, slot C wasn't committed yet. And the way this ring buffer works, this anti-ring buff that I designed, the way it works is that you cannot commit a slot D before you finish committing slot C. So it will make it wait until the thread until a thread on core 2 finishes processing item 3 and commits slot C. And this way you can have CPU core 4 running thread 4 and reading from this ring buffer Z, and it will be receiving these items in order. So you can have some heavy processing amortized across cores, and then you can just merge it on an additional core using some very quick operation and perhaps some decision making. It's just a fun exercise to do. Let's see what else can we do. We can also do mixed low and high latency. So what happens here is we repeat last exercise, but here we use on core number 4 we're doing some not wait-free operations, right? So we can see those blue spaces there on the diagram below. The CPU core number 4 is waiting in those blue spaces. It's just causing waits. Now we need to be aware that if we introduce any non-wait-free solution into this pipeline, then we can potentially jump the whole pipeline. Meaning that if core number 4 waits for too long to read from pipe, from ring buffer Z, then core number 3, which is writing to ring buffer Z, and core number 2, which is writing to ring buffer Z, they will be blocked on ring buffer Z because they will just, fill the ring buffer Z. They won't be able to write to it. And when that happens, they won't be also reading from ring buffer X. And when that happens, ring buffer X also becomes full because core 1 keeps writing and there is no more space to write. So you can jump the whole pipeline when you do that. So what you can do, you can progressively increase the waiting, times. So on core number 4, you can just do a jump from lock-free solution into, for example, this unbounded queue, which uses condition variable and mutex. And that should be sufficiently fast because you should be able then, take values from the ring buffer Z and just put them onto some, unbounded queue using mutex and condition variable without significantly affecting the pipeline, right? So that's an interesting fact. Let's look at something else now. So this is just estimated graphs. This is not real graphs, but just to show you more or less what we're expecting from ultra-low latency ring buffer as compared to single-threaded, processing of let's say market data and firing orders, for example. So normally, if you do it on single thread, you will have a very wide peak and it will also have long tail. And that is because what will happen is in the periods of a huge amount of data coming in from market, you will have data queuing into your, maybe your solution is using unbounded queue. And there'll be a lot of packets queuing into this unbounded queue, right? Because it takes so long to process and it's all single threaded. So you're going to have this, PNL loss due to latency, right? So this market data was so delayed that, if it wasn't delayed, maybe you would fire on it. You would say, oh, that's a good market price to fire, but it was so delayed that you weren't able to take it, right? And so that's how single-threaded solution suffers from this problem. And this multi-core pipelining solution essentially should amortize all this because it should be processing the packets as they're coming, and you have more space to do it in parallel, and it shouldn't be queuing like crazy like in this first case, right? So you should have more spiky output and generally more controlled. But I do not guarantee that. It all depends what is the whole solution. Very likely it's a combination because maybe this whole pipeline is used to actually read from some maybe hardware accelerated something, who knows. So that's just for your consideration of what you can do with this. The processing times, I don't really know. It depends on what you're using there. But the ring buffer itself can give you latencies of few nanoseconds, really, I think. It can give you like probably around 100 if there is cache coherency going on or something like this. And so if there is a clash and there is a cache coherency going. But I think if there is no issue, it can give you some very low latency. Pros, we get lower amortized latency because we start processing next item before we finish processing previous item. We amortize processing jitter, and we get better use of cache as each CPU core runs smaller portion of the code. The cons is we introduce latency in communication between CPU cores. This is what I said. But it's like you need to measure it. It can be 100 nanoseconds, it can be 10 nanoseconds, or maybe you will measure 0 nanoseconds. It really depends how is the whole pipeline going, and what is going on in the pipeline. Notification overhead. Yeah, so when one core is writing to ring buffer and another core is trying to read that slot, it's waiting for the slot to become available, because maybe nothing is available. It's waiting, right? So it needs to be notified, but we're not using here conditional variables. We're just using these atomic operations, and we spin. So this overhead will be really minimal, but there is some little notification overhead that requires maybe cache coherency to go into coherent state. Wake up overhead, right? So this is how much time it takes for this code to actually, that's actually the consumer thread wake up, right? So if you have two threads, one is to write into ring buffer notification, and the second is to wake up on the consumer side. So how much time, the notification is how much time it takes, how many nanoseconds in order for me to do the commit of my operation, commit of the write, how much time it takes, and then how much time it takes to do, begin read, So that's the wake up. Okay, so summary. Log-free and wait-free programming reduces thread synchronization latency to very small nanosecond value range. Yeah, so it is possible to go very, very low and play with nanoseconds. And it's all about cache coherency, memory barriers, atomic operations, maybe optimizations, how many memory barriers are there on the way, and changing the the rules of how memory barriers are enforced. Avoids context switching and putting thread into inactive suspended state. That's obvious. Log-free programming and wait programming is all about doing that exactly. Avoids deadlocks because there is no locks, so we don't have a problem with that. However, it consumes CPU power and awaiting change for shared state. So yeah, so we just eat energy, right? So you want to be fast, you want to be, go like those fast cars, then you have to consume a lot of fuel. Pipelining takes advantage of multi-core CPU architecture and allows us to process higher amounts of packets in given unit of time. Yes, that's true. We don't have, like, the packets won't be queuing so much, right? And reduces jitter by multitasking processing time. So we will be, for example, reading those packets in a more uniform way. We won't be like delaying that, like, if we put everything on single thread, as I showed you, we might be actually delaying when we read the packet, and that might be also bad. Adds only small amount of latency within range of few nanoseconds. Yes, that's what I just said. Monitor mutex and condition variables should be used on non-critical execution paths. Yeah, so that's your go-to solution, right? So the ultra low latency is something that that is to be used in controlled environment in the lab, in some specific hard and fast environment where when you know what's going on, when you know what cores you have, and all this details. When you're writing an application on your desktop, you probably just want to stick to mutex and condition variable, because this is probably the most convenient way of synchronizing threads, that doesn't kill all your machine, and to save energy, right? And that's smooth. Okay, so that's end of my presentation. Thank you so much for watching, and yeah, let's connect. This is my my GitHub and my YouTube, and this is where you can find me. Subscribe, like, comment. Bye.